Hi everyone. The goal of today's lesson is to learn how to calculate a rate of a reaction that is using laboratory data, so something that we would collect in the lab, and then how the coefficients in a balanced chemical equation play into a rate equation. So when we're looking at reaction rates, the term kinetics, which is what we call this unit in chemistry, is the study of how quickly a reaction is happening. And remember, kinetic energy is the energy of movement. So when we think about how fast a reaction has to occur, it's going to depend on the reactants that we have and their movement, right? So a rate of a reaction is defined as the change in concentration of a reactant or a product per unit of time. So you can see that that's shown here with this equation. Change in concentration over change in time. Now think about it like this. My reactants are going to turn into products as a result of a chemical reaction. So that means the concentration of reactants is going to decrease because it's going to get used up, and the concentration of the products is going to increase because I'm making products as I go through the reaction. So you'll see this little note that's put here. Place a negative sign in front of this expression if we're worrying about reactants. So if we're looking at a chemical equation and the data we have is for a reactant, it's going to get used up over time. So we want to use a negative sign in front of it to indicate that the quantity of it is decreasing. So if we were to graph concentration versus time, what we see that reagents, or what we call reactants, will go down as time goes on. So as time goes, I'm using up reactants and using them up and using them up to eventually there's a point where I don't have any left to use. This is why it has a negative slope here. And the positive slope is for the products. These are going to form throughout the reaction, and eventually that's all that's going to be left. We're not going to have any reactants left. We're just going to have products that we made. So again, if we are using reactants, we want to make sure we put that negative sign out in front of them. So this reaction, if we look at this graph, it starts off really fast and then it starts to slow down over time. So the question is, why? What's happening is for our reagents or our reactants, they are getting used up over time, right? So as they get used up, that means they're not available to react. As they are getting used up, or what's called depleted, they have less surface area for collisions. In order for a chemical reaction to occur, things need to collide, right? We actually have to physically make contact with one another. My reactants have to make contact. So if there's less of them available to collide, your reaction is going to take more time to occur. So we're seeing that as the reagents get used up, there's less surface area, there's less collisions, and the reaction starts to slow down, which is why we don't see this, like a nice linear graph, but instead we see this more so as this curve that we see. So how do we actually use this data to solve for something? So let's say we're looking at the chemical reaction 2NO plus chlorine gas yields NOCl. So what you're given here are two different times, your start, okay, and your ending time. You notice that in this chemical equation, this is a reactant, the NO, the Cl2 is also a reactant, and then our product is NOCl. And as you can see, when we go through 2 minutes of time, the two reactants get used up. We run out of some of them. And what happens to our product? It increases, okay? So just keep that in mind as we go through this problem. So we remember that the equation for defining rate and figuring out what the average rate is of something, it's the change in concentration over the change in time. And that's going to be C2 minus C1 over T2 minus T1. And in this case, we're trying to figure out the reaction rate for NO gas, okay? So we're only caring about this information that's in this highlighted yellow box and the time that we're working with. Okay, so I don't really care about the chlorine or the NOCl, only really care about the NO. So what I'm going to do to solve this is plug in these values. So it's a reactant. So if you remember from the previous slides, I want to put a negative sign out in front because it's a reactant. It's going to get used up. My ending concentration is 0.460. My initial concentration was 0.500. I'm going to put that over my change in time, 2 minutes minus 0 minutes. This forms negative 0.04 over 2.0, which equates to 0.02 moles per liter per minute, okay? So when we're looking at like concentration is moles per liter. So our units for this are moles per liter per minute, okay? So let's try another one. Same data we were using before. Now we're just going to look at one of our other reactants. So now we're going to worry about chlorine gas, okay? So in this case, slightly different numbers, but I'm still going to be just caring about what's happening here and what's happening here. So all these other blocks I don't really care about. So we know that rate is the change in concentration over the change in time, which is C2 minus C1 over T2 minus T1. So I want to plug in that number that's going to apply to chlorine, and we remember it's a reactant, okay? So keep that in mind. It's a reactant. So I want to put that negative sign out in front because it's a reactant. So my ending concentration for chlorine is 0.480. My initial concentration was 0.500. My ending time was 2 minutes. My initial time was 0 minutes. I find that this is equal to, where am I here? Negative 0.02 over 2.0, which is 0.01 moles per liter per minute, okay? And then finally, if we're looking at our third material here, which is the NOCl, this is a product. So when I'm trying to calculate the rate and use that rate equation, I don't have to put a negative sign out in front. I can instead just put my values. I don't have to worry about that negative sign. So we have C2 minus C1 over T2 times minus T1. So 0.040 minus 0 and 2.0 minus 0. This becomes 0.04 over 2, which is equal to 0.02 moles per liter per minute. Okay, so what we've done through these 3 practice problems is we've looked at how much we're either going to use up in the case of our reactants or how much we're going to produce in the case of our NOCl. And this is calculated per minute of the reaction time. So as I let time go forward, I would be increasing my concentration this much every single minute of the NOCl. So we're going to now compare our answers. If we think back to our previous slides that we had when we were determining the average rate for NO, which was our first reactant, the answer we got was 0.02 moles per liter per minute. When we were looking at the chlorine gas, it was 0.01 moles per liter per minute. And our last one was 0.02 moles per liter per minute. So if we look at our balanced chemical equation, how are these values related to the coefficients that we see out in front of our balanced chemical equation? And what we see here is that we look at our chlorine, which doesn't have a coefficient out in front. It's just the number 1. Its rate is half as much as the other ones. So what that means is I'm reacting twice as much of the NO, and I'm producing twice as much of the NaCl in comparison to the chlorine. So I can use those balanced chemical equations to compare the rates. So I don't have to go through and do these equations time after time after time. Instead, what I can do is solve it for one of them and then compare the balanced coefficients, because those will be related to one another. They are equal to one another. So that ratio in comparison is what we'll see happening. So again, if it was 0.02, 0.01, 0.02, I look at my coefficients that are out in front, which was 2, 1, 2. And if we look at these values, these correspond with one another and what we see with our actual data. So essentially, I'm using up twice as much NO as I do chlorine, and that's because it has that 2 right out in front there, okay? So when we look at our balanced chemical equation, let's say we're looking at this one, just in general, when a reaction starts, which substances would have negative rates, meaning we need to change the sign out in front of them? That's going to be A and B, okay? Those are my reactants. If the rate of reaction A is 0.048 moles per liter per minute, what will be the reaction rate for C? So if we look at A compared to C, it is a 2-to-1 ratio, and that's what I can see with those coefficients that are out in front there. It's 2-to-1. So if I know that A is 0.048, the rate of C has to be half of that. So I'm going to half it, 0.024, okay? So because our reaction rate is half as much for C as it is A, that's why I halved this number here. Let's try another one, okay? If we look at the reaction rate of B being 6.3 moles per liter per minute, what will be the rate of C? So we compare B to C, it's a 3-to-1 ratio. So if B is 6.3, what would that be equivalent to? A third of it, we divide it by 3, it would be 2.1 moles per liter per minute. And if we look at number 4, which two substances will have the same rates? Which of the two have the exact same coefficients? It's A and D. Okay, so hopefully by now you understand how to calculate rate as a result of looking at that data, but you can also look at those coefficients and figure out what a rate should be based on how they balance each other out.